Hello everyone, I'm James and welcome to episode 12 of the OpenGL tutorial series. Today we're going to finally start working on the fabulous water.
Let's take a look at a real life example. Here is a bowl full of water. This is actual water, okay? So, the water looks mostly transparent, at least from the top. As you can see the inside of the bowl. It barely looks like there is any water at all because the water is very still and there's no distortions. If we look at a shallow angle though, we can see that the water suddenly is reflecting a lot. And if I put my fingers, you will be able to see the fingers reflecting in the water. This is called the Fresnel effect. When we look from the top, the water looks transparent. When we look from the side, the water looks more reflective. So we somehow need to get a reflection. However, there is more to water. To make it look more interesting, we can add distortions. So let's imagine there is wind blowing. If I go and blow, well, you didn't see it, you can see it a little bit. Or if I put my finger and stare it a bit, you can see that there are distortions. And if we look at the reflection of the window, you can see that the reflection of the window is getting distorted. However, not only the reflection is getting distorted, if we look straight down into the bowl and I start to stare it, you can see that even what is under the water starts to get distorted.
I did a couple of things off screen. First of all, I created a static function in the mesh class that creates a quad. And this is the code that creates the quad. It creates 4 vertices, 6 indices for the triangles, and it calculates the tangents and returns the mesh. The normals are specified here. So, then I also created the water material, which is a new material type, and all it does is loads 2 shaders, a water vertex shader and a water fragment shader, which I defined here. The water vertex shader is very simple. It takes in the position attribute, it takes in a uniform for the world view projection, and all it does is it transforms the vertex position with the world view projection and outputs it to the output. The water fragment shader is almost even simpler. All it does is outputs the color blue. So back in the code, I created an entity. I set it to -4 on the y-axis, so it's slightly below the camera. I also set the rotation to the default rotation, so a quaternion identity, and I scaled it to 20, the same size of the terrain. In fact, coming to think of it, I'm going to use the terrain size constant. Actually, it's not a constant, but you get the idea, Also, I created it using the quad and the water material. And if we run now, there we get a blue quad. How can we get reflections on this quad?
So this is our scene right now. To get a proper reflection, we need to take a photo of the scene from under the water. The y distance between the camera and the water needs to stay the same. There is a little problem, however. When we render the scene from under the water, the camera's vision may be occluded by some object. It's actually pretty easy to prevent this. All we have to do is render only what is above the water. We can easily tell OpenGL to cull the scene by a particular plane. We also want to take a photo of what is under the water, so that we can later distort that photo. We don't need to do anything fancy, all we have to do is take a photo from the camera's original position. This is not good enough, however. Let us say there's some stupid object in the way of the camera. That object will occlude the view of the camera again. So all we have to do is cull everything above the water clipping plane. How do we define this clipping plane? A clipping plane is made from a direction and a distance. Let us add this framework in our source code. We'll start by modifying the entity's render method. This will take in two more parameters. The first one is a boolean, which specifies whether we want to clip or not. I'll default it to false. The second parameter is the actual clipping plane, which I'll also set to a default value. If clipping is true, we'll enable GL clip distance 0. We can enable multiple clipping planes. One will be good enough for our purposes. If clipping is false, we'll disable GL clip distance 0. Next we'll set the clipping plane uniform, which we'll add soon. We haven't added a method to set a 4D vector uniform yet, so in the shader class we'll add the new method. Setting a 4D vector uniform is very similar to setting a 3D vector, just with the additional W component. In the diffuse vertex shader, we'll add the 4D vector uniform for the clipping plane. There is a float variable called the clip distance. This variable is accessible in the shader. When this variable is set to a positive value, nothing is clipped. If the value is negative, everything will be clipped. If we set the clip distance to the dot product between the world position and the clipping plane, we will get exactly what we want. So we first need the world position. We'll get this by multiplying the world matrix with the vertex position. Finally, we'll set clip distance 0 to the dot product between the clipping plane and the world position.
I don't want the water to be part of the entities list, so I'm going to create a field for it. It's going to be a shared pointer to an entity, and I'll call it water. In scene.cpp, I'll set water equal to std make shared of entity with these arguments, with the same arguments we had before. At the end, I'll call water render with the view projection. View projection, the ambient light, the light direction, and I leave the rest as default. So let's define a clipping plane. I'm going to call it clipping plane, and I'm going to set it horizontally, so a horizontal clip plane. Now I need to set the distance. So how much do we want this? I will set it to be, well, let's say 0, so it will clip everything below 0, everything below 0 on the y-axis. So now let's pass in render inside. We still want it to false. We'll do the clipping, we'll set it to true, and we'll set the clipping plane for the clipping plane. And now if we run, there you go, it worked. So there's not much being rendered because most of the terrain is below 0, but as you can see, everything below 0 is actually clipped, which is perfect. Now we want ideally the clipping plane to be at the height of the water. That's very easy to fix. All we do is set this distance to the water transformation and the y-axis. Sorry, the position dot y. And now everything below the water is going to be clipped. Well, I screwed up something, however, because that's not working right. Maybe I have to... Yeah, I think I have to make it negative. Yeah, of course, I have to make it negative. What was I thinking? Alright, yeah, perfect. Now we get here, and as you can see, below the water, everything is clipped. Now how do we clip everything above the water instead? All I have to do is negate this one. And now if we run... Actually, I screwed up something again. So I believe we have to negate this we have to negate it. So since it was already negated, we'll make it positive. Yeah, okay. And under the water, as you can see, the stuff under the water is here. So there you go, we clipped above the water and below the water. Finally, we can go ahead and start working on doing frame buffers and doing reflections.
So how can we get a reflection of the scene on the water surface? There is this concept in OpenGL of frame buffers. We already have a frame buffer, and that is the screen. So the frame buffer is made of a color buffer and a depth buffer. We can create additional frame buffers, which are called frame buffer objects. We can then add what is called a color attachment and a depth attachment. These are basically textures. Because when you think about it, the screen is kind of like a texture, it's an image. So what we can do is in the frame buffer object, we render the scene, and then we use the frame buffer as a texture. And that, my friends, is how we can achieve a reflection on the water. We render the scene another time, and we render the scene in this frame buffer object, and then we use this frame buffer object as a texture on the water quad, which gives us a reflection. I created a frame buffer class. We'll first add a constructor. The first two parameters are the width and height. We'll include stdint.h. The next parameter is a boolean, which specifies whether we want a color attachment or not. The next parameter is also a boolean. This specifies whether we want a depth attachment or not. The last two parameters are the sampling mode and the wrapping mode of the attachments. We'll need to include glue. We'll store the width and height in the class. I'll store the frame buffer ID, the render buffer ID, and the two attachments. We'll need to include texture.hpp. I'll add a destructor, getters for the attachments, and a bind method. Let us implement the constructor. We'll first initialize the width and height fields. Next, we'll create a frame buffer and bind it. We'll now check if color attachment is true. If it is, we'll set the color attachment texture to a new texture. The width and height are going to be the width and height of the frame buffer. We won't set the texture's pixels, so I'll pass in null pointer. For the internal format, I'll pass glRGB8, and for the format, I'll pass glRGB. Finally, I'll pass the sampling mode and wrapping mode for the last two parameters. Now we need to tell OpenGL to render the texture we just created. To do this, we'll call glFrameBufferTexture2D. The first parameter is the target, which we'll set to glFrameBuffer. The second parameter specifies which attachment we want. We'll set this to glColorAttachment0. The third parameter is the texture target. In our case, it's glTexture2D. The fourth parameter is the texture ID of the color attachment. We'll get the ID from the color attachment texture. We need to make the frame buffer class a friend of the texture class, so that we can access that ID field. The final parameter is the level, which we don't care about, so we'll set it to 0. Now we'll check if the depth attachment is true. Creating a depth attachment is very similar to creating a color attachment. The internal format is GLDepthComponent32 and the format is GLDepthComponent. The other arguments are the same. Next we'll call glFrameBufferTexture2D, this time with GLDepthAttachment for the attachment type and the depth attachment ID for the texture ID. If there is no depth attachment, we still need to store the depth buffer in a render buffer. So we'll create a render buffer and bind it. We then need to tell OpenGL how to store the render buffer. We do this by calling glRenderBufferStorage. The first parameter is the target, which in our case is glRenderBuffer. The second parameter is the internal format, which I'll set to GLDepthComponent32. The last two parameters are the width and height, so I'll pass the width and height parameters. Next, we'll tell OpenGL to use the current render buffer for the frame buffer. The first parameter is the target, which is GL frame buffer. The second parameter is the attachment type, which in our case is GL depth attachment. The third parameter is the render buffer target. In our case, this is GL render buffer. The last parameter is the render buffer ID. Next, we'll unbind the render buffer. The last thing we need to do in the constructor is check for errors and unbinding the frame buffer. We'll need to include IOStream. The destructor is very simple. If there isn't a depth attachment, we'll delete the render buffer. Finally, we'll delete the frame buffer. Now let's implement the bind method. First, we'll bind the frame buffer. Next, we'll bind the render buffer if there is no depth attachment. Finally, we need to set the viewport to the size of the frame buffer. This is very important. With that, the frame buffer class is done. Now we need a method to bind the Windows frame buffer. So in the window class, we'll add a new method called bind frame buffer. The first thing we'll do is unbind any frame buffer object that might be bound. We'll need to include glue. Next, we'll set the viewport size to the size of the window. In the scene header file, I'll add two new fields. These are going to be the reflection frame buffer and the refraction frame buffer. Let us initialize the reflection frame buffer. The first two parameters are the width and height. I will hardcode them to 1024. We do want a color attachment, so we'll set the next parameter to true. We don't need the depth attachment for the reflection, so we'll set the next parameter to false. The next parameter is the sampling mode, which we'll set to GL linear. The last parameter is the wrapping mode, which we'll set to GL clamp to edge. The refraction frame buffer is almost exactly the same. However, I'll set the depth attachment to true, because we'll need it in the future. In the scene header file, I'm going to add a new method which renders all the entities except for the water. This will take in three parameters. The first parameter is the camera. The second parameter is a boolean, which when true enables clipping. The third parameter is the actual clipping plane we want to clip on. I'll default this to a default GLM vec4. I'll also rename the camera to main camera. This will remove a bunch of confusion. Now I'll move this code into the new render entities method. Instead of getting the view projection from the main camera, we'll get it from the camera parameter. Instead of hardcoding true for clipping, I'll pass the clipping parameter. In the render method, we'll get rid of the clipping plane variable. Next, we'll put the main camera under the water. I'll store the water height, the camera position, and the camera rotation in variables. Now we'll calculate the distance between the camera and the water. Then we'll need to move the camera on the y-axis by the distance multiplied by 2. Next, we'll flip the rotation of the camera on the x-axis. A very easy way to do this is by negating the x and z components of the quaternion. Now we'll bind the reflection frame buffer and render everything above the water. Next, we'll revert the camera position. Now we'll bind the reflection frame buffer and render everything below the water. Next, we'll bind the window frame buffer and render everything without any clipping. Finally, we'll render the water entity with the main camera's view projection. Now it's time to change the water material class. This will contain the reflection texture and the refraction texture. We'll initialize these fields in the constructor. Finally, we need to bind these textures and send them as uniforms. In the scene constructor, we'll initialize the water material with the reflection frame buffer's color attachment and the refraction frame buffer's color attachment. In the water fragment shader, let us add the two new uniforms. Next, we'll sample the colors from both the reflection texture and the refraction texture. Then we'll output the mix of both colors. When sampling the textures, we didn't specify any texture coordinates. What texture coordinates should we use? Let us try the simplest method. In the vertex shader, we'll get the texture coordinates from the vertex and send them out as a varying variable. In the fragment shader, we'll take in the texture coordinates and use them when sampling the texture.
If we run right now, we get kind of a mess. We're getting some sort of refraction and some sort of reflection. However, it's a mess. So to fix it, it's actually pretty easy. Apart from sending out the texture coordinate, which we'll use in the future, I'll send out another variable. I'll send out a vec for the projected texture coordinates. And I'll set this to the world view projection matrix multiplied by the vertex position. In fact, I'll pass in the projected text chords as the GL position. Now in the water fragment shader, we'll take in first of all these projected texture coordinates and we'll do some calculations. I'm going to create a vector called text chords and I'm going to set it to the xy division by the v projected text chords dot w. So we're swizzling the vector and getting the xy components, and then we're dividing it by the w component. This is called the perspective divide. We'll also need to bring these text chords between 0 and 1. Right now they're between -1 and 1. This is very easy. All we have to do is multiply by 0.5 and add 0.5. We're almost done, and we can use this directly for the refraction text chords. But for the reflection we want to flip these texture coordinates, so I'll put negative text chords. Sorry, text chords.x and negative text chords.y. Now if we run, there you go. Actually it's not working. The refraction texture is working, but the reflection texture looks absolutely terrible. It turns out I made two mistakes. First of all, here instead of minus text chords we want 1 minus text chords.y. That will flip it properly. There's another mistake however. Right here, where we're sending water height, we should set negative water height. If you run now, there you go. It's working fine now. Awesome. And that, my friends, is the end of this video. In the next video, we're going to add distortions and specular lighting to our water. If you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell. With that, thanks for watching and goodbye.